solving trig equations. Let's just recap all the different identities and formulas that we've seen so far. So there's our compound angle formulas. First of all, for sine, sine, cos, cos, sine. If it's a sine, it's a sine. Cosine, cos, cos, sine, sine. If it's not the sine, it's not the sine. And tan, tan plus tan on 1 minus tan, tan. So they were our compound angle formulas. From there, we got our double angle formulas. So sine 2 theta, 2 sine theta, cos theta. Cos 2 theta, which we talked a bit about yesterday, has 3 different ways we could write it. Cos squared minus sine squared. 2 cos squared minus 1, which allowed us then to integrate cos squared, because we get cos squared is a half of 1 plus cos 2 theta. Or 1 minus 2 sine squared, which allowed us to integrate sine squared, because we could change that to a half of 1 minus cos 2 theta. And tan 2 theta, 2 tan theta on 1 minus tan squared theta. The t results, which you can also think of as the half angle results, and that's where we let t equal tan theta on 2, so half the angle. Then tan theta becomes 2t on 1 minus t squared, which really is, when you think about it, just the double angle formula for tan. But then from there we could work out sine theta was 2t on 1 plus t squared, and cos theta is 1 minus t squared on 1 plus t squared. Then we had products to sums. So there's our first one, 2 sine A cos B. Now, because it goes sine cos, it must have come from the sine compound angle formula. So that's why we have sine A plus B plus sine A minus B. 2 cos cos must have come from the cosine formula, and that's the one that goes cos A plus B plus cos A minus B. And then the sine sine also came from the cos, but this time it's a little bit different, you'll notice. Cos A minus B minus cos A plus B. Or another way of thinking about it, so it sort of keeps the plus always as the first one. You can think of it as minus cos A plus B plus cos A minus B. But again, remember, those ones will be on your formula sheet. So if you are in doubt, check and make sure you get it right. These ones are not on the formula sheet, where we go the other way, the sums to products. So sine A plus sine B, 2 sine half sum cos half diff. Cos plus cos, 2 cos half sum cos half diff. So they both end with cos half diff, and it starts with whichever one we're looking at. So addition of the sine starts with the sine, addition of the cos starts with the cos. And then cos minus cos, that's a bit different because we're doing subtraction instead of addition. So because it's a bit different, we end up with sine and sine, even though we're doing cos minus cos. That's a bit different. So we get minus, that's a bit different. The other ones were positive. So minus 2 sine half sum sine half diff. So there are some of the products, and I've asterisked that to remind you that they aren't on the formula sheet. So we can use all those sorts of ideas to help us solve trig equations. So the idea when solving it, we want all the angles to be the same. So all thetas or all 2 thetas or whatever it happens to be. Then we have a look at the range, and we've got to match the range to the angle. Normally they'll say something like theta's in between 0 and 360. So if you're working with 2 theta, then you've got to look for answers between 0 and 720. Then get the trig functions the same. So that might involve using a trig identity or something. And then once we've got that, we can just treat the trig as if it's a pronumeral, and we just solve like a normal equation. But if in doubt, unsure what to do, fall back to the idea of, can I just change things to sines and cos? Always check your answers, because especially with trig equations, remember when you're transforming your equation into a different equation to make it easier to solve, sometimes you create new solutions, which are solutions to the new equation, but might not be solutions to the original equation. So always check. All right, let's start with a very basic one. Cos 2 theta equals a half. So straight away I can see, well, I'm looking for answers between 0 and 720. I'm going around the circle twice. We're in the first and fourth quadrant, of course. The acute angle would be 60 degrees, because cos of 60 is a half. So 2 theta will be in the first quadrant or the fourth quadrant. So it'll either be the acute angle or 360 minus the acute angle. So that gives me 60 and 300, but we're going around twice. So we add 360 to both of those answers. But that's what 2 theta is. Now we can divide by 2 and get our answers for theta. So that's how we would have originally looked at it before we saw all our trig identities and what have you. But now, of course, we could do it this way. Cos 2 theta equals a half. I could use one of my cos 2 theta results. Which one did I choose? I went for the 2 cos squared theta minus 1 is equal to a half. That then becomes cos squared is 3/4. So cos is plus or minus root 3 on 2. Well, plus or minus means I'm in all 4 quadrants. Look, we get the butterfly. The acute angle in this case is now 30 degrees, but I'm in all 4 quadrants, so I actually end up with the same 4 answers, of course. Sec squared equals 3 tan. Well, x, the angle is the same. Let's try and get the trig the same. And we've got an identity, of course, that says sec squared is 1 plus tan squared. So we change that to 4 plus 4 tan squared. It becomes now a quadratic equation because tan x now is the pronumeral. That one factorizes, thank goodness. And we get 2 possible answers. Tan x is minus 1/4 or tan x equals 1. So minus 1/4, second quadrant or fourth quadrant. And let's work out the acute angle. I've done it to the nearest minute, 14 degrees 2. So we end up with our 2 answers there, 165.58, 345.58. Tan x equals 1, that's positive, so it'll be in the first or the third quadrant. The acute angle in this case is one of our exact ones, 45 degrees. So there's another 2 possibilities. Don't leave your answer like that. Okay? Remember, you're presenting your solution for someone else. Make it easy for them. Tie it all together. There's all our possibilities. 45 degrees, 165.58, 225, and 345.58. Cos 2 theta is 4 cos squared theta minus 2 sine squared theta. So we've got a couple of things happening here. We've got different angles. We've got 2 thetas and thetas, so we've got to fix that up. And we've got different trig as well. We've got cos and sine. I'm going to use cos squared minus sine squared for this one. So cos squared minus sine squared. Then I'm going to rearrange that and get 3 cos squared is sine squared, because now I can use our relationship of sine on cos is tan. And so I get tan squared is 3. So tan is plus or minus root 3. Again, I end up in all 4 quadrants this time. And that's an exact value. So 60 degrees is the acute angle, giving us 60, 120, 240, 300. This one comes from, quite old now, 2000 HSC. Cos 2 theta is sine theta. So again, I've got a choice of what to use for cos 2 theta. Because I know I want to end up with the same trig, it makes sense for this one to use the, there it is, 1 minus 2 sine squared. Because now they're all sines. It is a quadratic equation, so let's make it look like one. And does that factorize nicely? Yes, it does. So 2 sine theta minus 1 sine theta plus 1. 2 possibilities. Sine theta is a half, so we're in our first 2 quadrants. That's an exact value. It's, sine, 30 degrees, isn't it? So 30 degrees, giving us 30 and 150. Sine being negative 1's a boundary angle. So if you think of your curve, there's only going to be one answer. And that'll be when we're down here, that's going to be 270, isn't it? Yeah. So I was about to say all 4 answers. There's only 3 for this one. So 3 answers, 30, 150, and 270. Oh gosh, let's go even further back. 1992. Goodness me. 2 sine squared is sine 2 theta. So I've got a 2 theta and a theta. First thing to do is resolve that problem. Well, I really only got one choice now, because sine 2 theta is 2 sine theta cos theta. Well, it's quadratic. Factorise out the sine theta, or the 2 sine theta, and I get sine theta is 0, or sine theta equals cos theta. Sine theta equals 0 is a boundary angle. The thing to watch out for here is we've got both ends of the domain. A lot of people forget to put the 360 in. But if 0 is a solution, so is 360. You've got to get both ends there. So 0, 180, 360. The other one I can turn into tan is 1. And that's our exact value of 45 degrees. So we get 45, 225. So we actually end up with 5 answers for this one. Now, I've been using degrees for all those, but of course, it's probably more likely we're going to end up with radians. Sine. So this is one of our products to sums. So sine must have come from the cosine function. So we end up with minus cos 4 theta plus cos 2 theta. Well, they're both causes, but the angles are different. But 4 theta is, of course, double 2 theta. So I can use a double angle result on that and get all the angles in terms of 2 theta. So the angles are the same, but they're 2 theta, not theta. So I'm going to be looking for solutions between 0 and 4 pi, going around the circle twice. Well, let's solve it. Factorizes nicely. 2 possibilities. Cos 2 theta equals 0. That's a boundary value. We actually end up with 4 possibilities there because we're going around the circle twice. They are my answers for 2 theta. So divide by 2, I get my possibilities for theta. Now let's do cos 2 theta as a half. We're in quadrants 1 and 4. The acute angle is pi on 3. And again, going around twice, that's 2 theta. Divide by 2. Now let's put all of these answers down. Whew. I like to put them in order. So there you go, pi on 6, pi on 4, 3 pi on 4, and so on. Quite a lot of answers for that particular question. Let's look at a more recent HSC question, as in last year's. This was interesting. The numbers a, b and c are related by the equation a equals b minus d and c equals b plus d, where d is a constant. Show that sine a plus sine c over cos a plus cos c is tan b. Okay, well, let's substitute in what they told us a and c are, because we've got to get b into this somehow. Use our sum to product, that's the one that's not on the sheet. So that's why a lot of people probably would have done the compound angles. But if you remember your sum to product, so sine, 2 sine, half sum, cos, half diff. And on the bottom, cos plus cos, 2 cos, half sum, cos, half diff. We've got cos minus 2d on top and bottom, so that'll just cancel. So we've ended up with sine on cos, which is tan. Okay, part B of the question then. Hence, or otherwise, should you choose to use a different method, solve this equation. But look at the similarity to what we just did, hence the hence. So in this case, b minus d, remember, was a, and b plus d was equal to c. If I play around with that, I get that 2b is a plus c, and b is a plus c on 2. Why did I do that? Because what we just proved, that all of this will just be the tan of b. So how do I work out b? Well, b is a plus c over 2. So in other words, this becomes tan of 11 theta on 14, yeah, way to make the numbers nice for us, is equal to the square root of 3. Now, theta goes between 0 and 2 pi, but we're looking for answers for 11 theta on 14. So we have to work out, we're going to go between 0 and 11 pi on 7. The question now is, where is 11 pi on 7? Which quadrant are we talking about? Well, it's certainly more than pi, so we keep going. 3 pi on 2 would be the end of the 3rd quadrant. So it's in the 4th quadrant somewhere? Is that what it is? Okay, let's have a look. Quadrant 1 and 3, we're only looking for answers anyway, so we should be okay. So 11 theta on 14 is pi on 3 or 4 pi on 3. Therefore, theta is 14 pi on 33 and 56 pi on 33. Wasn't that just a little bit mean last year? Horrible numbers. You imagine people doing it, they're just going to think you're getting it wrong. What? On 33? Okay, so 11A, we'll play with trig equations.